Welcome to Lecture 8 of Computer Aided Engineering Design. This is our last lecture in solid modeling. I'm going to be covering three topics here. One, to prove the generalized Euler Poincaré formula. Two, to give you an example on parametric solid modeling. And the last topic is going to be a little note on regularized Boolean operations. First, a little informal proof of the generalized Euler Poincaré relation. V is the number of vertices, E the number of edges, F the number of faces, L the number of loops, S is the total number of shells that can have their own genus value or own number of handles, G is the number of genus, and the left hand side is equal to 0. We try to prove it informally, of course. We have seen and informally proved this relation before. The left hand side is the Euler characteristic for polyhedral solids, and the right hand side is the Euler characteristic for smooth solids, where G would be the number of handles and C would be the number of boundary components. Let's start with the proof now. Let's consider a sphere and triangulate it. We know that this polyhedral solid is going to be having the Euler characteristic of 2. Let's take off a triangular face from the spherical surface to introduce a boundary component. When we do that, the number of faces get reduced by 1, and so the number of vertices minus the number of edges plus the number of faces equals 1. What we do now is we try to build up a prism, a triangular prism, on this opened up surface. What have we done? We have introduced 3 plus 3 edges. We have introduced 4 faces, the first face, the second face, the face on the back side, the third, and the top face. And we have additionally introduced 3 vertices. So in this Euler relation, we have 3 additional vertices, 6 additional edges, and 4 additional faces, because of which the right hand side becomes 2. In the next step, what we may want to do is we may want to bulge out this triangular plane of face into a spherical face. In the Euler relation, nothing changes because this thing is a valid solid. And in fact, this solid is homeomorphic to a sphere. I could as well have constructed a triangular prism inside the parent sphere, and I could have bulged out this triangular face into a spherical surface. Again, nothing would have changed. We would still have a solid which is homeomorphic to a sphere, clearly, because the Euler characteristic tells us that its value is 2. What we might want to do now is let go of this triangular prism and cover up the outer sphere and the inner sphere to leave out a spherical void within a spherical solid. Let's see how. When we let go of this triangular prism, we are deleting 3 edges. We are not deleting any vertex, and we are deleting 3 faces. In addition, we are reintroducing 2 faces, one face on the outer sphere and one on the inner sphere. So the left hand side, b minus e plus f, in that we will have no change in the number of vertices. The number of edges will get decremented by 3, and the number of faces will get decremented by 1. So the right hand side will be 2 plus 2. I can keep on introducing spherical shells or spherical voids inside the parent sphere, which would help me generalize the right hand side of the Euler relation b minus e plus f as 2 plus 2 s prime. S prime would be the number of shells that I have introduced into the parent sphere. I can combine the previous relation with this one and have a more general formula as b minus e plus f equals 2 plus 2 s prime minus 2 times g minus c. These are the terms that I get from previous smooth solids. I can manipulate this right hand side further. I can factor 2 outside, and I can rewrite the right hand side as 2 times within parenthesis 1 plus s prime minus g minus c outside the parenthesis. Once again, s prime is the number of additional shells that I have introduced within the parent shell. I can combine 1 plus s prime together and write it as s, suggesting that s would be the total number of shells. If I compare this relation with the Euler Poincaré formula, I have the number of vertices, the number of edges, the number of faces, the number of shells, and the number of handles in place. All I need to worry about is to introduce this term here in the Euler Poincaré relation. We come back to polyhedral solids with the same relation that we had derived, or we had proved informally, of course, last time. And we try to understand what a loop is more formally. A loop would be any closed curve sketched by traversing all the edges of a face or a boundary component. If you look at this figure here of a block, we have the top face opened up by a boundary component. So this is the first loop. We traverse the 4 edges of the face which is nearest to us. The second loop, the third loop, traversing the bottom face. The fourth loop, traversing the top face. Fifth loop, and the sixth loop. And then we'll have a loop corresponding to the boundary component at the top. If I introduce any other boundary component, I'll introduce a corresponding loop with that. Now let's see how introducing different boundary components would affect the Euler Poincaré formula. We start with the formula, and now we segregate, or we divide S into two parts. We say S is 1 plus S prime for certain reasons, which I'll tell you about later. If I introduce a boundary component, I open up this top face, because of which, and of course I'll have a loop here, because of which the number of faces will decrease by 1, so that the total number of faces for this polyhedral solid will be 5, but the number of loops will be 7. Let's verify the above Euler Poincaré relation. We have 12 vertices now, 16 edges, 5 faces. We have no interior shell S prime, for which S prime is 0. We have no handles, because of which G is 0. And we have one boundary component C. We see that the above Euler Poincaré relation is satisfied. If I introduce another boundary component and a loop with it, we are opening up one more face, because of which we actually have 4 faces but 8 loops. Let's verify the Euler Poincaré relation again. We now have 16 vertices, 20 edges, 4 faces, again no interior shell S prime, no handles, and now we have 2 boundary components. So C is 2. What have we noticed? Each time a boundary component is introduced on a face, the number of faces will decrease by the same amount. If I have introduced, let's say, 2 or 3 boundary components, the number of faces will decrease by 2 and 3 respectively. We can use this observation in this manner. We first assume that the number of faces F in the Euler Poincaré relation are the same in the original solid without boundary components. So we assume that the original solid is a perfectly valid polyhedral solid which does not have any boundary. Whenever a boundary component C is introduced, or whenever a number of boundaries C are introduced, there is a corresponding decrease in the number of faces. In a sense, the decrement in the number of faces will be equal to the number of loops minus the number of original faces. And this difference, L minus F, will be the same as C. Once we know that, we can adjust the Euler Poincaré relation as this: V minus E plus F minus, within parenthesis, L minus F minus 2 times, within parenthesis, 1 plus S prime minus G plus C. Once again, each time I increase C by, say, 1, I decrease the number of original faces by the same amount, 1. I will repeat here that C is the same as the number of loops minus the number of faces. Question: what if another boundary component is introduced on the same face? That is, a face will have 2 boundary components in total. This is the first one with a loop. and this is the second one with a loop. Let's see how the previous relation fares. Well, we have this relation here. We compute the number of vertices as 16, 8 from the original solid, 4 here and 4 here. The number of edges will be 20, 12 from the original solid, 4 from this boundary component, and 4 from this boundary component. The number of faces in the original block will be 6. The number of loops will be 8 now, 6 corresponding to the original solid and 2 corresponding to these two boundaries. So this is 8 minus 6. Well, S prime is the number of shells within this solid. Since there is no shell within this solid, S prime is 0. So this is minus of 2. And the new number of boundary components introduced is 2 boundaries. We see that the left hand side turns out to be 0. And so the Euler Poincaré relation holds. What if now a third boundary component is introduced on the same face? The number of vertices will now be 20, 4 additional. The number of edges will again be 4 additional. The number of faces in the original solid will remain the same. The number of loops will now get incremented by 1. So this is 9. And the number of boundary components, C, will again be 3 because there are 3 boundaries here. We again see that the Euler Poincaré relation holds. Introducing a boundary component on the same face is equivalent to borrowing a boundary from a different face. And that is possibly the reason why this relation does good. Finally, we get the Euler Poincaré formula for valid solids without any boundaries when C equals 0. We now come to the second part of the lecture. This is an example on parametric solid modeling that Mr. Shailesh Pandey has helped me prepare. Here, I would like to showcase different features that many solid modelers have. Since we have done a workshop on the design of a study lamp or a table lamp, I'll use the same example. We are going to be trying to design a study lamp with all prismatic features. First, the design of a base. We'd like to have a trapezoidal base. We carve this trapezoid from this rectangle here. We have a trapezoid now. We are going to be extruding this cross section into the third dimension, that is, the dimension towards 0. To get a solid feature. The height of this trapezoidal base is about 10 units. Next, we'll try to carve out certain features on this base. So these circular features might correspond to, say, holding pens. This rectangular pothole would correspond to, say, holding erasers or pens. We're just trying to play with the design here. We have specified the relations between these two edges. We ensure that these two edges remain parallel, even if we change the dimensions of this rectangle. Once we sketch out these cross sections on the base, we try to intrude these cross sections into the base to get circular potholes and a rectangular pothole here. the depth of these potholes is about 5 units. This is how we see different potholes. We can actually change the colors of different parts if we want. Next, we'll try to design a prismatic connector that connects the base to the bulb holder. We have this rectangular feature on the top face of the base, and we have the circular arc. The idea is to get the connector, again, of prismatic shape to this nonlinear sweep. This rectangular cross section is going to be swept along the circular arc. We do that and we get the connector of this shape. Next, we try to design a bulb holder. We have a trapezoidal cross section here, which we have extruded along this vertical direction by some amount. This is another view of the lamp, and we are going to be shaping up this bulb holder slightly differently. We'll introduce a taper along this direction at the base here. After we do that, we will introduce a shell like structure to represent the bulb holder. The thickness is about 1.5 units. We have a basic lamp design ready. These are different relations that Shailesh had used to design this lamp. Parametric solid modeling allows us to choose different features in the design and modify them locally so that we do not have to undergo the entire painstaking design procedure. Let's try to understand parametric solid modeling through the following slides. First, we choose this circular feature and we play with the size of this pothole. We increase the size. When we do that, we get this pothole of a slightly larger size. This window here represents the history tree when creating this design in the text form, not in the graphics form. One can choose any feature from this history tree or double click the corresponding feature in the graphics window here to implement whatever changes he or she has in mind. Now we are trying to introduce the chamfer on the base. After we do that, our design appears like this. We can change colors if we want. Let's now try to enlarge the base of the lamp and observe how the design looks. We have different dimensions here which are related to each other. If we change any one or two of these dimensions, our base will get enlarged. This is one key feature of parametric solid modeling. We have to have relations between different features in place. We can choose this face as well as the face behind it, and we can increase the distance between the faces. When we do that, this is how our design looks. Next, Let's try to play with the size of the bulb holder. Once again, we choose the face nearest to us. In this part, we choose the face right opposite it, and then we enlarge the distance between two faces. Let's try to play with the bulb holder a little more. We increase the vertical dimension now. Again, in a similar fashion. Choose the top face, choose the bottom face, and increase the distance between. We have left this hole right there. We can bring this hole a little upward along the vertical direction. A very similar procedure. When we do that, we have now got the hole at the right place. Let's now play with the neck of the lamp. So in the previous example, what we had was we had a rectangular cross section swept along a circular arc. Here, we'll have the same cross section, but swept along a line, a straight line. When we do that, we get a straighter neck. We can elongate the neck if you want to get a new design. In a sense, we are parametrically trying to change different geometric features of this design without actually having to redesign the entire lamp from scratch. And it is this feature that is very nicely employed in complex solid modeling. We can have a group of designs through parametric solid modeling. Once again, if you look at these 5 designs, the basic topology or connectivity of these designs remain identical. It's only the shapes and sizes or different features which are changing. As we intend, we can present these designs to the customers and let them choose which of them they would like. This is the third and the final part of this lecture. A little note on regularized Boolean operations. This is the slide that I had covered in the previous lecture. I had emphasized that there were certain pitfalls or drawbacks of the raw Boolean operations. We take a block or a cube, we take a cylinder, we align them or transform them in such a way that one of the faces of the cylinder sits on one of the vertical faces of the cube. The two solids are A and B, and if you try to compute the intersection, we get a disk. This is a lower dimensional feature, two-dimensional in nature, and it does not represent a valid solid. And it was this example that I had used to introduce regularized Boolean operations. Let's look at a few more examples. We have a cube, and now we have a cylindrical primitive sitting over the top face of the cube. The cube is solid A, the cylinder is solid B. If we try to compute the union between the two solids, we get this solid with a common edge between the two primitives. This is a non-manifold solid, because if you look at this common edge, it is sharing 4 faces. This is face 1, this is face 2, This is the third phase, and this is the fourth phase. If we recall the definition of manifold solids, there we had used an open ball. If we place an open ball here, anywhere on this edge, we'll see that the intersection between the open ball and the solid will result in two intertwined disks, which cannot be deformed into a single disk, for which reason it is a non-manifold solid. The third example of a block and of the same cylinder, solid A, solid B. We now compute A minus B. We'll get a block with a slight singularity on the top face. The common edge between the cylindrical primitive and the block will not be present on the block. If you see this, there would be a very thin slit that will open up the top face of the block. Same example now, a block and a cylinder sitting over it. We try to compute what is B minus A. Once again, we'll possibly have a cylindrical surface with a little slit opened up right there. So these are certain singularities or anomalies which are associated with raw Boolean operations. To eliminate these anomalies, we had proposed regularization of Boolean operations before. So a regularized union will be like this. We compute the raw union, we compute the interior of the result, and then we perform the closure operation. In the closure operation, we actually compute the union of the interior as well as the boundary of a solid. Likewise, regularized intersection. We compute the raw intersection, we compute the interior of the result, and again we perform the closure operation, taking the union of the interior and the boundary. The regularized difference is performed in a similar manner. We compute the raw difference, take the interior of that, and then perform closure. All these operations make a lot of sense if we think about solids as a set of points occupying a finite volume in the Euclidean space. But I have emphasized that solids are seen by virtually all solid modelers by their corresponding bounding surfaces, as per the extended Jordan's curve theorem. This is the question that I asked myself last time. How do we perform regularized Boolean operations when dealing with only bounding surfaces, when we do not have a set of points to deal with? Because only then these operations will make sense. With only bounding surfaces, possibly these operations will be difficult to be performed. I can only conjecture at this time, but this is what my conjecture is. All we need to do is we need to make sure that the result of the raw Boolean operations is a bounding surface by itself. In other words, the result of the Boolean operations is a perfectly valid solid. How do we do that? Well, we have a tool. Recall the winged edge data structure. All we need to do is ensure that the winged edge data structure is properly structured. Let's revisit these 4 examples and see how the data structure can have anomalies which can be detected, and then we can conclude that the results may or may not be valid solids. Let's take a look at the intersection example first. Block A, cylinder B, intersection would give us a disk. Now if you recall, for any valid solid, polyhedral or non-polyhedral, with different surface patches constituting the solid and different surface patches stitched at the common boundaries, a valid solid will be one for which each boundary edge will have not more and not less than 2 faces incident to it. In this example here, if this is a boundary curve, it will have exactly 2 faces incident to it. Now, if we look at the result here, it's an open disk. This outer boundary has only 1 face incident to it. It does not have a second face associated with it. And this thing can be detected in the winged edge data structure, and correspondingly the result can be eliminated or can be categorized as a non-valid solid. Let's take a look at the union example here. Block A, cylinder B. If we compute the union, we'll have a common edge between the cylinder and the block. We know that it's a non-manifold solid. If we look at this common edge, this will have, as I mentioned before, 4 faces and not 2 faces associated with it. So corresponding to this edge, the winged edge data structure will complain, and we can detect that complaint, and we can say that this solid is not a valid solid. Just in case if some of you are having visualization difficulty, let me try to sketch the features around that common edge on the board. This is the common edge. This is the first face from the block. This is the second face from the block. This would be the third face from the cylinder. And this would be the fourth face from the cylinder. 4 faces. Let's take a look at the third example again. The difference between the block A minus the cylinder B. Look at this slit here, which opens up the top face of the block. This corresponds to the common line between the cylinder and the block. There are 2 kinds of singularities. One, you can think of the slit as composed of 2 edges which are very, very close to each other. And second, of course, this is opening up the top face. because of which the block will not be bounded anymore. So there are two edges, and if you look at any one of the edges, that edge will have only one face incident to it. If you look at the edge on the left, it will have only the left face which is incident to it, and likewise for the right edge. So the winged edge data structure can detect both the singularities. If the two edges are very close to each other, it will complain accordingly, and if there are less than or more than two faces incident to a single edge, it will complain as well. Likewise, the fourth example. If we subtract the block from the cylinder B minus A, we'll have the slit right here at the lower region on the cylinder. Once again, very similar problems. Two edges very close to each other, and each of the edges will have only one face incident to it. Both these singularities can be detected when computing the winged edge data structure.